In this video, we're going to start with an example of interval estimation when we have small sample sizes. So we discussed the concepts and for doing this in the last video, so if you haven't seen that, you probably should watch it first. All right, but we're going to just jump right into things. I'm going to read off this kind of problem. I'm going to read it twice. Once I'm just going to read it through. The second time we'll read it and put up the important pieces of information and then go from there. All right, so it says, suppose you work for an online news publication and are tasked with finding out readership numbers. You record the number of daily website views for 14 days and find a mean of 27,864.291 and a standard deviation of 1,527.337. Find the 90% confidence interval. All right, so now we're going to run through that again. We're going to pull out those important pieces of information. All right. Suppose you work for an online news publication and are tasked with finding out readership numbers. You record the number of daily website views for 14 days, right? So that's going to be important. Those 14 days, that is our sample size. So n equals 14. Let's see, with that glare, y'all might not actually be able to see that. Right, so n equals 14, and find a mean of 27,864.291. So that is the mean, the sample mean. And a standard deviation of 1,527.337. Obviously that is important, that is the standard deviation, so that's what we're going to want to grab that as well. And we are doing this at the 90% confidence interval. All right, so we're being asked to find a 90% confidence interval, so we're doing it at the 90% confidence level. All right, so now that we have all of that information, we can go ahead and start working towards getting our estimate. All right, so we're going to just follow our formula. So remember, x bar plus or minus t alpha divided by 2 comma degrees of freedom. That's all one thing. That's our critical value. And times s over the square root of n. All right. So we're going to start with our sample mean x bar 27,864.291. We're going to add and subtract our critical value. So t, then we need alpha divided by 2. So if our confidence level is 90%, that means our alpha is 0.1, right? And when we divide that by 2, which we need to do here for these confidence levels, we're going to get 0.05. All right, so just once again, just so everybody knows where that's coming from, right? A 90% confidence level, that's going to correspond to an alpha of 0.10, or so kind of, we get, if our confidence level is 90%, then what remains is that 10%, put that to decimal format, that's your alpha, all right? So 0.1. Then, because this is a confidence interval, we're going to divide that alpha by 2, so 0.1 divided by 2 is 0.05. Right? Then we'll need to find our degrees of freedom. Our degrees of freedom are n minus 1, so our sample size minus 1. Our sample size is 14. 14 minus 1 is going to give us 13, so our degrees of freedom are 13. Then we are going to multiply this critical value by the standard error. And we're going to calculate the standard error by dividing the standard deviation by the square root of the sample size. Our standard deviation is S, or 1527.337. And our sample size is 14. So we're going to divide by the square root of 14. One thing I want to note here is that once we get to this part and we've included these degrees of freedom, right, some students are going to want to subtract 1 from our sample size over here as well. Do not do that, right? We do that for our degrees of freedom. We don't do it for anything else, all right? So this should be n, right? We're taking the square root of n, not n minus 1, all right? So once we've gotten to this point, let's condense some of this stuff down. Right, when we're getting our test statistic, or excuse me, our critical value, this t, right, we're going to go to our t distribution. We're going to go along the top until we find t 0.05. Right, we know then that that's the column our critical value is in. Then we'll go along the first column and we're going to find those 13 degrees of freedom where that row and column intersect. That's going to give us our critical value. All right, and what we should find when we look on our chart is 1.771. All right, when we finish up this, we kind of do this division, right? We're going to get, for our standard error, 408.198. Right, when we multiply our critical value and our standard error together, we get our margin of error, which is 722.919. Right, once we have that, the last thing to do is to add and subtract our margin of error from our sample mean to get our upper and lower bounds. So then we will have our interval estimate. So the 90% confidence interval will be 27,141.372 for our upper boundary, for our lower boundary, and 28,587.210 for our upper boundary. And once we get to this point, we're essentially done. If we're just asked to find the confidence interval, we're done once we get to this point. If we're asked to interpret that confidence interval, the interpretation for a confidence interval like this is identical, right, to the way we would do it as we've done it previously, all right? So whatever our confidence level is, we're that percent confident that the population mean for whatever we're looking at is between our upper and lower boundaries. All right, so for example, with this one, we're looking at daily website views. So we could say I am 90% confident that the population mean for daily website views is between 27,141.372 and 28,587.210. right? So that would be how we would interpret that confidence interval. All right, so that is all for our actual kind of our example. So now we're going to look at precision and sample size. So with our confidence intervals, right, the more narrow the confidence interval is, the better the estimator that we are using. So we want our confidence intervals to be as narrow as possible, partially just because it gives us a better idea of where that population mean is going, right? So if we think back to one of the first couple of videos that we put up for this, we talked about how we could define an interval that contains any population parameter ever, right? Negative infinity to infinity. We talked about how that wouldn't be very useful because, you know, it doesn't really tell us anything. Right, again, talking about, you know, having a service person that's going to come fix something in your home. If they tell you I'll be there between 8 a.m. and 8 p.m., that's not very helpful. It's not very useful. We would want a more narrow window, right? If they told you instead of that, they told you I'll be there from between 1:30 p.m. and 2 p.m., that's a much better interval, right? That's a much smaller interval, right? Gives you a better idea of when they're getting there, right? Even if they're a little bit early, a little bit late, at least, you know, that's going to be, it'll be closer to that. It's going to give you a better idea. So how do we get smaller intervals, right? Is there anything that we can do to get a smaller interval as kind of researchers, as people studying whatever we're doing, as statisticians? Right? And the answer is yes. All right, and the way that we're going to do this is through the margin of error. Right, so I mentioned the margin of error a couple of times. It is the thing that we're adding and subtracting from our sample mean and our interval estimators, right? Here we just got the version for when we're using the Z distribution. We don't really need to worry about Y, but we're just going to stick with this for now. All right, so when we're looking at this margin of error, right, this is what's going to determine how wide or how narrow our confidence interval is, right? It's not going to be the population mean, which is the only other thing that is in that calculation, because the population mean is off by itself, right? It's not going to, it's the central point, right? It's in the middle. It's going to be in the middle of that confidence interval no matter what. So the only thing that's going to determine the width is this margin of error, right? There are three things that could contribute to the width of the margin of error. All right, so let's talk about those and see what we can do about them. All right, first I want us to talk about sigma, or the standard deviation. So this is true whether we're talking about the population standard deviation or the sample standard deviation. All right, but it is, well, this is especially true. This is true about the population standard deviation. All right, the population standard deviation is fixed. Right, we might not know what that population standard deviation is, right? Or even if we do, it's fixed. It is a single number. It is what it is. You cannot change that. All right. That's the same for the sample standard deviation as well. Once you've got that sample standard deviation, it is what it is, right? You could get you go out and collect a new sample and maybe get a different one, but that you don't really have any control over what it is, right? It just is the standard deviation for that sample or for that population. There's nothing you can do about it. So that's not going to be a fruitful avenue to go down to make our intervals narrower. All right, next let's look at our critical value, T alpha divided, or Z alpha divided by 2. Right, if we're looking at this, all right, can we change it? Yes, right, we've got, we can change our critical value by changing our alpha. Right, there are three commonly used ones that we're going to use, right? Or three commonly used confidence levels, right? 90%, 95%, and 99%, right? But when we change those, right, we're also changing the strength of our interval estimate, right? Because if you are at 90%, right, excuse me, let me back up, right? If you're at 99%, your interval is going to be wider than if you're at 90%, right? So if you go from 99% down to 90%, you're going to get a smaller confidence interval, but we also know that a 99% confidence interval is a stronger result. You're more confident, right? It's a better result than a 90% confidence interval, right? You're going to be more confident that your population mean is in the interval when you're at 99% than when you're at 90%, right? Part of the reason for that is because that interval is wider, all right? But, so in order to make a narrower interval just based on our critical value, we have to sacrifice strength, right, or confidence in our estimate, right? Plus, there's only 3 commonly used confidence levels, so you don't have a lot of option, and if you're trying to make it narrower, you're only ever going down. So that's probably not a great option either. All right, so again, it is changeable, all right, but if we're changing it to make it our interval narrower, we're going to sacrifice some strength. All right, so that leaves one thing left, all right, our sample size. Can we change our sample size? Absolutely, all right. We can absolutely change that sample size, and we can make it whatever we want, right? Especially if we're going out and collecting data, we can collect as much data as we want to, right? Also, another good thing about N, we already know that it's going to have an effect, right? Because, right, we talked about how N, right, changing N changes this term, our standard error. We talked about that in chapter 8, right? As our sample size increases, the standard error decreases, right? Because this is going to get bigger and bigger. It's going to make the whole term smaller, right? And if this term is smaller, right, that means the whole term is going to be, your margin of error is going to be smaller, the smaller your standard error is. So we can change our sample size. We can use that to make our confidence interval narrower, right? The way we're going to do that is by increasing our sample size. So just in general, the higher your sample size, the better your estimates, the more accurate they're going to be, the more precise. That's just, we've kind of touched on that in chapter 8, right? And once again, just kind of restating it here. But let's say that you want a specific margin of error, right? You want, let's say that, think about one of the places you've probably heard the term margin of error quite a bit and really recognized it was, one, anytime statistics are being thrown around, sometimes they'll offer a margin of error, especially if people are trying to predict something, especially if they're trying to predict political races, right? So when people are doing polls for political races and they're predicting who's going to win, or they just say, this is what the polls say, that 40% like candidate A, 28 like candidate B, so on and so forth. They usually offer a margin of error, right? And most of the time that margin of error is 0.5%, right? 1/2. All right, so how do they know, how do they get to that, consistently get to that margin of error, right? Well, they can do that by getting a large enough sample size. So, but how do they know how large of a sample size they need to get, right? That's what we're going to look at right now. All right, essentially what we're going to do right now is we're just going to take this equation, this equation for the margin of error, and we're going to solve for N. All right, so we're going to multiply both sides by n. Right, when we do that, we're going to cancel it out over here on this side, move it over here. So margin of error times the square root of n equals z alpha divided by 2 times sigma. And then we're going to divide both sides by the margin of error. All right, you could put this whole side under the margin of error, so z alpha divided by 2 times sigma over the margin of error. I just like the way this looks better, so that's the way I do it, but you don't have to, right? Either way it's fine, right? And then the last step will be to square both sides, so we get rid of this square root on our sample size. All right, and so we're left with n equals z alpha divided by 2 times sigma divided by the margin of error squared. All right, and this formula is going to give us the sample size needed to get a desired margin of error with a given confidence level. All right, so let's take a look at an example. All right, so as I have been doing, I'm just going to read it once, and then I'll read it again and put up the important pieces of information. All right, so suppose you know that the standard deviation for the weight of an apple is 13.712 grams. What is the sample size required to estimate the sample mean with a margin of error of 5 with a 99% confidence level? All right, so suppose you know that the standard deviation for the weight of an apple is 13.712 grams. What is the sample size required to estimate the sample mean with a margin of error of 5? So that is our, and we don't need the grams there, we just need the number, right? So our desired margin of error is 5 with a 99% confidence level. So all right, now that we have this information, and this is all the information that we need, we can go ahead and set up our equation. So n equals z alpha divided by 2, right? So 99%, so our alpha is 0.01. That would make alpha divided by 2, 0.005. Times our standard deviation, which is 13.712. Divided by the margin of error, which is 5. And then we're going to square everything inside. All right, the z-score would be the critical value would be 2.576, right? So once we have that, we can punch all of this into our calculator, and we should get n equals 49.906. All right, so this would be the answer that we would get once we run everything through the formula. All right, when we are doing this, this is another instance of where we need to round up at the end. All right, so to get the this margin of error with our desired confidence level, right, we need to round the sample size up. In this case, we would round it up to 50. All right, so we would need a sample size of 50 to ensure a margin of error of 5 for the sample mean of the weight of apples at a 99% confidence level. Right? This is one of those cases where we're always going to round up to the nearest integer. Right? So even if this was 49.206, we would still round up to 50. All right, that is it for chapter 9. I will see you guys in chapter 10.